Welcome to our goal-based scenario prototype called the kiosk crash investigation. A goal-based scenario is a learning approach where learners acquire knowledge by working towards a meaningful goal within a realistic situation. Instead of simply reading notes about programming concepts, learners actively apply their knowledge to solve a problem. In our prototype, learners take on the role of a lead system investigator. Their goal is to identify the cause of a self-service cafe kiosk system crash that has disrupted cafe operations during peak hours. This incident report introduces the scenario and presents the problems that need to be investigated, such as lost orders, queue issues, and system errors. To solve the case, learners must complete 4 investigation leads that focus on important programming concepts, including input process output, conditional statements, loops, and debugging. By embedding learning within a realistic mission, the goal-based scenario helps reduce learning friction by making learning more engaging, meaningful, and easier to understand. After opening the case file, learners enter the investigation HQ. Here, they are assigned the role of lead investigator and can view the 4 investigation leads. Each lead represents a different programming concept. Breaking the lesson into 4 separate cases reduces cognitive overload because learners focus on one concept at a time rather than learning everything at once. These progress indicators and mission structure also increase engagement by providing clear goals and a sense of achievement. In Lead 1, learners investigate the order log by reconstructing the input, process, and output sequence. The learner drags code fragments into the correct categories. For example, user data belongs to input, calculations belong to process, and displayed results belong to output. Immediate feedback is provided whenever an item is placed incorrectly. This helps learners learn through active experimentation rather than passive memorization. This activity addresses learning friction by making the abstract IPO, which is input, process, and output concept visual, interactive, and easier to understand. For the next lead, which is Lead 2, learners investigate a malfunctioning discount system. They compare 2 code fragments, an if-else statement, and a while loop. The learner must identify which control structure correctly match the decision flowchart shown below. The visual flowchart helps students connect programming syntax with logical decision making. This reduces confusion that beginners often experience when learning selection structures and conditional statements. In Lead 3, learners investigate why the cafe queue became frozen. The challenge requires reconstructing a loop that processes customer orders correctly. By analyzing the missing logic, learners develop computational thinking and understand how iteration works in real-world systems. Using a realistic queue management scenario makes looping concepts more meaningful and easier to remember compared to traditional textbook examples. For the last lead, which is Lead 4, learners perform debugging to identify the exact line that caused the system crash. The screen presents source code, a variable trace table, and multiple possible fixes. Learners analyze the execution process and discover that a variable name was typed incorrectly, resulting in a name error. This activity develops debugging skills while helping learners understand variables and program execution. The trace table also reduces learning friction by making invisible program process visible and easier to follow. After completing all 4 leads, learners successfully solved the case and closed the investigation. Overall, the goal-based scenario transforms programming concepts into a detective investigation. The use of storytelling, missions, immediate feedback, visual aids, and real-world scenarios reduce learning friction by increasing motivation, reducing cognitive overload, and helping learners connect programming concepts with practical applications. As a result, learners are more engaged and can understand input, process output, selection, iteration, and debugging concepts more effectively.